In this video, might be our last video, Nuclear Physics 4 or Atomic Physics 4, we will look at some more practice questions. There's no theory, just the practice questions. And I'm going to look at a few more radioactive reactions problems. So let's look at some questions. So here I have a first question we're going to look at, and they say a mercury 198 nucleus is bombarded by a neutron which causes a nuclear reaction, and they show you the equation for the nuclear reaction. What is the unknown product, particle X? So the sum of the protons on both of the sides of the equation should match. So in our case, we have the sum of the protons is 80. On the other side, it has to be 80 as well. So from here, I see that Z, the atomic number, has to be 1. And the same has to happen for the nucleons. The sum of the nucleons must be 199. So that means the sum of the nucleons on the other side is also 199. And then from here, I see that A is going to be equal to 2. So the element I have is hydrogen with 2 nucleons, 1 proton, and it has a positive 1 proton charge. It is called deuterium. It's the isotope of hydrogen atom. The other elements that you see in this problem is Hg, which is mercury, stands for mercury, and Au is gold. You don't have to memorize all those. The periodic table usually given for you on the AP exam, but you have to know how to use the periodic table to get the information. But usually it's not, the chemistry part is not tested. And they ask you to find the number of nucleons, neutrons, and protons in the atom, or define the atomic number or mass defect, but they usually don't ask the questions about what kind of element it is, and if they do, you have periodic table to look in. In this problem, they say, can the following nuclear reaction occur spontaneously? And they give you the reaction, and then they tell you that the mass of the nitrogen nucleus is 13.9992 AMU, and then they also give you the mass of the oxygen is 16.99947 AMU. So in order to answer this question, we first have to figure out the mass equivalent of the disintegration energy, and for that one we have to calculate the mass defect. So I'm looking for the mass of the alpha particle, and that would be the mass of the helium minus the mass of 2 electrons, because it's the ion of the helium atom. So I have the mass of the helium from the periodic table that you see me using here. So this would be the mass of the helium atom. So here I have the mass of the helium atom minus the atomic mass of the electron, and that is 0.000549. I have to subtract 2 of mass of the electron, so I'm subtracting 2 of them from the mass of the helium ion. So here I see that they already give this number, so this is nitrogen nucleus that they give you, and we have that number. So I didn't have to do calculations for this number or look for in the table. It's already given, so I can use that one. And then on the other side we have oxygen. So let's see how much of the oxygen is going to be. They give you as well. So mass of the oxygen is given too. So here I have the oxygen part. And you don't have to write AMU. You can write, instead of AMU, you can write just U. And the last part we have is hydrogen again. So we have the mass of the hydrogen that we can look up through the table, periodic table. And it is given that it is 1 positive proton, so that is an ion, so it doesn't have an electron. So if I take the mass from the periodic table, atomic mass from the periodic table, I can subtract the mass of the electron. So in the periodic table, it would be 10079 minus the mass of the electron, 1, which is 0.00549. I'm just going to round it here, and I will get 1.00735 AMU. So that is the mass of the hydrogen ion. So now we're going to look at the differences of the masses before the reaction and after the reaction. So here I have the mass before and now the calculations for the mass after. And that gives me 18.00205 AMU. So now I can calculate the differences in masses before and after. So when I subtract these two masses, I see that there is a difference in two masses before and after the reaction. And I see that the mass after has more, there's more mass after than before. So that means that the reaction is non-spontaneous and energy must be supplied in order for this reaction to proceed. If I want to convert this number into the energy, I multiply the mass by 931.49, and that will give me the energy needed for this reaction to occur, and that gives me 1.26 mega electron volts. So I used the mega electron volts for conversions. I should have added mega electron volts. So I get 1.26 mega electron volts of energy needs to be supplied into this reaction for it to happen. The process that powers the sun and upon which all life on Earth is dependent is the fusion reaction. Then they give you the expression of the reaction and they give you the protium or the hydrogen with one proton AMU. And in this reaction you see that the protium is being split into an alpha particle, 2 electrons, 2 neutrino, and a gamma energy release. The mass of the alpha particle is given 4.0015 AMU, and they ask you to ignore the mass of the electron and of the electron neutrino as well. So we're going to look at the mass defect in this problem. What we need is to find the mass difference between the reactions and the products. So we need the mass of the 4 atoms of the protium on the left side, compare it to the mass of the alpha particle, 2 electrons and 2 neutrino, but they say you can ignore those. So here I did the calculations that I need to do, the mass of the 4 the protium atoms, and then I have the mass of the alpha particle and the mass of the electrons, and now I'm gonna subtract them, and I will get so in this reaction we see that the mass is positive, so that means this this reaction will release the energy, and convert this number into energy I have to multiply it by 931.49 mega electron volts, and that will give me how much energy is released in this case. So we have 24.7 mega electron volt is released in this case during this reaction. They ask you how much energy per proton went into this from this reaction. So if I divide this both sides by 4, that will give me the energy released by proton. So I have 6.2 mega electron volt of liberated energy per proton. I will do a few questions where you have to balance the equations with the reactions. So in this case you have 238 uranium with the alpha particle release, and then they ask you what other element is added. So here I will have the new element that is going to be released. So you have or the daughter element. So you have the total number of the proton must be equal to 92. So that means this element has 90, and the total number of new nucleons before and after has to be equal to 238. So you have 234 in this case 234 in this case, and that element is thorium. I don't memorize these elements. I have to look up into the periodic table. So you will be given the periodic table if you have to specify what elements they are. What you have to look is at the number of the, or atomic number, the number of the protons per element, and you can find that it's the element number in the periodic table. In the next question, I have beta negative decay. So in this case, when I have beta negative decay, I'm going to have antineutrino and a new element. So I will have some element plus the antineutrino. This element will have the atomic number 91, because when they add, they have to add to 90, the number that was before. And the number of nucleons together should be equal to 231. So in this case, you have 231. And if you check periodic table, you will see that 91 proton element is called protactinium. So it has 91 protons and 231 nucleons, means protons and neutrons together. The next decay is the alpha decay, because I have an alpha element right here. So alpha particle is released. So again, the new element is gonna have the sum of the protons on the left and right side must be equal to each other. So this is the left side, this is the right side. So this new element will have to have 89 protons, and the sum of the nucleons together also has to be matched. So that means on the right side I have to have 227 nucleons, 227. So you have protactinium splitting into the alpha particle and the daughter element with 89 protons called actinium. In the next reaction, you have carbon 14 splitting into nitrogen 14 and an extra element, and this element will have a -1 number of the protons, so that means it is an electron. So if it is an electron, it looks like that's going to be the beta negative decay, and if you have beta negative decay, you also have the antineutrino released. And the number of nucleons on both sides matches as well. Next decay is the alpha decay. I see that I have an alpha element on the other side, and I have to figure out that alpha element comes with which other element, element X. So the sum of the protons on both sides must be equal to 4, so that means this one is going to be 2, and the sum of the nucleons on both sides must be equal to 8, so that means I have a 4. So right here, so that means I have 2 helium atoms, and maybe one of them or 2 of them alpha particles. In this problem, they ask you to balance the following nuclear equations. So we have potassium 43 with 19 protons that is going to split into calcium 43, 20 protons. So I have to balance this equation, and in order to balance my number of protons, looks like that's going to be the negative beta decay or an electron. So the number of the nucleons on the left and the right side match, and the negative beta decays comes with it, that's an electron. So we're going to have the antineutrino as well. The next problem, we see uranium splitting into thorium, and again I have to have the number of the protons on the left side and the right side match. So I'm gonna have an element that has 2 protons, and it will also have 4 nucleons, and that is the helium ion and or the alpha decay. And so again, and I see that my number of nucleons on the top also have to match together to the number on the top and the right and the left, and this indicates that it is an ion with a 2 positive proton charge. For the next element, I have carbon 12, and it's splitting into boron 11. So the two elements have to have, again, the two sides have to have the same number of the nucleons and the same number of the protons. So this element has to be an electron with a negative 1 in place of the protons and 0 as muons. In this case, I think there is a typo. It should be boron isotope. So because they both have to add to 12 on in their nucleons, so this should be boron isotope with a 12. And for the last problem that I have here, the number of protons on both sides must be equal to 7. The number of nucleons on both sides has to be equal to 13. So that must be a 0 and a 1, a positive 1. And that can only happen with the positive beta reaction. And with the positive beta reaction, you also have a neutrino coming with it. And in this question, they ask you which of the following represents the beta decay for 210 bismuth element. And what I have is polonium and bismuth on both sides, and the number of their protons has to match as well. So I see that the only one that has the matching number of the protons is the fourth choice, and then the only number that has the matching number of nucleons is also for the fourth choice. And in this case, because it's positive beta decay, I'm also gonna have a neutrino in this case, so that would be your beta positive reaction. I think I'm gonna stop this video at this point. If you find more practice questions that you would like me to record or explain, please bring them to the classroom or email me so I can record another video. And thank you for watching, and I will see you in my next videos.